Good morning, everyone. We're going to start today's lecture with a non-lecture, basically with a review for the midterm two. So just to get everyone oriented, reoriented, and get everyone on the same page. Remember, the midterm two is going to post 12:01 tonight, basically Thursday morning at 12:01, and will be available till 1 p.m. on Saturday. Similar to the first exam, there is 30 questions, a mixture of multiple choice and true false. I don't anticipate, much like last time, it'll take anyone near the amount of time, but I've allotted a 2-hour window for everyone to do the exams, and then 4-hour windows for those who requested more time. If you need more time, please let me know. I'm happy to make an accommodation and make it extend the time period. The only issue is, again, that once you log in, it's sort of set up that you stay logged in. For those who do well on the last exam, and that's very many of you, I think you should expect more of the same setup. I don't think there won't be any surprises, there won't be any major changes. Again, I highlighted the things in the lectures and in the weekly worksheets, as well as in the review sheet that I want you to focus on. And I think, broadly speaking, you're going to see the quiz focus very much on those things. Maybe not exactly all the questions asked the same way, but very much the same questions. So what I thought I would do, just in the interest of getting started, is I might just go through the review sheet first, and then at the end people can ask questions. That way we're not starting with questions, then I'm answering some of the review sheet and going back to it. But I'll try to highlight the key things here first. If anyone has any questions during as I go through the review sheet, please stop me. Better to sort it out then. But rather than just taking general questions now, I'll go with this first. But again, should be available tonight, open through Saturday, flexible when you take it, and there will be no new lecture on Friday to allow people dedicated time to complete the midterm two if they so choose to do it at that time. So. All right, I'm going to get started. The materials part of this lecture actually included a little bit of discussion about the end of earthquakes, but I actually have just sort of left that off the midterm two to keep you focused on everything from tsunamis through volcanoes up through coastal hazards and into rivers that we got to on Monday. So you'll see that's what's in the review. That's what's being in the exam. There won't be any sort of new questions about earthquakes, other than, for example, how they can play a role in causing tsunamis and things like that. So first major topic we covered as part of this midterm or second exam, well, it was tsunamis. Obviously, these are major coastal hazards. Some of the things I want to highlight here is the types of the types of occurrences that lead to tsunamis are most commonly earthquakes. We spent a lot of time talking about the Boxing Day earthquake in 2004 or 5, I can't remember the year, in Indonesia, where you had a major displacement of the Indian and Eurasian plates that led to a large tsunami that impacted Indonesia dramatically and many parts of the Indian Ocean as well. Earthquakes, by and large, are the most common, or one of the most common triggers for tsunami events. And again, that's often caused by displacement of water by the earthquake event. That causes a major displacement locally. With tsunamis, the waves are transmitted very quickly, often approaching the speed of sound or even a bit faster than that. But remember, the key thing here, and I think I had this described incorrectly in one of the quiz questions, is that, or the answer key was wrong for the quiz questions, is that when that happens, the tsunami waves travel at very rapid rates with very low amplitudes, very low wave heights. As a result, they're very difficult to detect deep in the ocean. As the energy gets close to the shore, as you see the coastline getting, the body of water getting less and less deep, shallower and shallower, closer to the coastline, that energy that's being rapidly transmitted horizontally gets transferred to vertical height, and that's what causes the massive waves you see related to the tsunamis. So in addition to earthquakes, underwater landslides are another issue. Slope failure. Remember, we talked about, I won't test you on this, so I don't know why I'm talking about in review actually, but remember, we talked about angle of repose. About 57 degrees is the maximum angle. That's a stable cliff. If it gets steeper than that, eventually it'll fail. and often that happens in underwater areas. We talked about this in terms of example in Alaska, where an underwater landslide led to a major tsunami event. Again, it's all about the displacement of water. Similar volcanic eruptions. Typically, when you have a large amount of volcanic material blow out of the side of a volcano, enter into a body of water, it can lead to a tsunami event. And then the last one, of course, are catastrophic tsunamis from meteorite impacts. Obviously, these are could be the most devastating, but are not as common as the other three. And certainly, we hope that's the case into the future. So I sort of already alluded to this, but again, the speed of tsunamis are initially incredibly fast, horizontally transferred away from the displacement of water in all directions. So again, if it's a tsunami occurred by a landslide or a volcanic eruption in Hawaii, it can impact all of the Pacific Ocean that's not shielded from those waves. But as the tsunami gets into shallower bodies of water and as it approaches the coastlines, the speed of the tsunami's lateral transport decreases rapidly, and that exchange is accommodated by a mass balance of increasing height that moves towards the shore, that moves shoreward. So in general, there are lots of areas that can be influenced by tsunamis. Any place near the coastlines is not immune. Landslides can occur in the Atlantic Ocean, and we talked about that in terms of the risk in the Atlantic from volcanic island failures. But the major region of tsunami risks are in the Pacific ring or rim of fire. That's the same for tsunamis, for volcanoes, and many other and earthquakes, which we won't talk about in this exam in any major way. But in general, geology happens near plate boundaries, and remembering that the ring of fire is plate boundaries surrounding the Pacific Ocean, where there's more or less subduction on all sides at large. That leads to great potential for earthquakes, tsunamis, and volcanoes in those areas. So maybe I'll just take 1 second here. Any questions about tsunamis in specific before I go on to talking about volcanoes? I know it takes a moment to type, but I'll come back to it if I hear any questions. Otherwise, I'll assume everything's okay for tsunamis and move on to the volcanoes for now. So volcanoes, again, like the earthquakes, tsunamis, most common along the Pacific Ring of Fire. Some of the key hazards with volcanoes I wanted to talk about comes back to intrinsically understanding the viscosity of the magma. Remember that temperature and silica content dictate how fluid the magma is. Now, low viscosity, something like water, you pour it, it would flow downhill. High viscosity, you can think of peanut butter or toothpaste, or even things that are more sticky than that are more viscous, and they tend to explode. It's a key aspect that leads to most of the hazards of volcanoes. Depends on the viscosity. While temperature does play a role, by and large, the biggest variable that's going to determine the viscosity of a given magma is its silica content. And the higher the silica content, the more viscous, the more slow moving. The more slow moving, the more explosive it's going to be, or greater potential for explosive behavior, which is where most of the volcanic hazards actually come from. We talked about the different types of volcanoes. Shield volcanoes tend to be formed by low silica magma. They're typically called basalts, although I won't test you on those words. And the important part of that low silica magma is when you pour it out onto their surface, it's going to flow easily. And as a result, think about pouring a glass of water on a desk. The viscosity is very low, and the volcano will spread out really easily, be very broad with gently slopes, and be very massive volcanoes from low silica volcanoes. So most of the global, mid-ocean ridges, areas that have basalt lavas like Hawaii, their shield volcanoes are going to be very massive. They're the largest volcanoes in the world, and they can spread out over great distances based on that low viscosity, low silica content. So please do remember that if it's in shield volcanoes, you can think of it as being a shield, broad and flat, as opposed to a composite volcano, which kind of looks more like what you think of as a volcano in your elementary school arts and crafts projects. The alternative of the the common types of volcanoes, I see a typo here, is a composite volcano. And composite volcanoes, again, are steeply sloping, and they're formed from more silica-rich magmas. So typically these are formed near subduction zones where you're seeing interactions of the mantle and crustal materials that increase the silica content. Key thing is these tend to be much narrower and higher locally, although the shield volcanoes can be have a lot of elevation accumulated over time, like the Hawaiian Islands. And these tend to be very silica rich. The important part about this from composite volcanoes being silica rich is that means that the viscosity can cause things to sort of plug up. When lava stops flowing, it can cool down and solidify. And when that happens, there's often potential to build up pressure, or magma pressure, gas pressure, steam pressure behind that plug. And as a result, you can obviously see very explosive volcanism from composite volcanoes. So to reiterate this, magma viscosity is the biggest variable that determines volcanic risks. An answer to that statement would be true. And in general, explosive hazards increase with increasing viscosity. Okay, so outside of this explosion hazard, there's some reasons that these explosive volcanoes cause a great deal of concern, or can at least change, the Earth's surface that impacts sustainability and things like that. One of the major ways that volcanoes can influence life on Earth, we spend a lot of time talking about this with volcanoes in society, is the fact that particularly in explosive volcanoes, composite volcanoes, silica-rich, typically near subduction zones, and it can be oceanic, or oceanic crustal subduction zones. When they explode, a lot of pressure can build up, and that explosion can transmit a lot of energy, as well as transmit particles and sulfur dioxide, in particular, into the Earth's stratosphere. Key thing here is that ash dust, and SO2, if it reaches the stratosphere, can have major climate forcing implications because it can block solar radiation, increase the amount of solar radiation that's reflected back to space, and as a result, there can be major cooling from these events. So we talked about this about the summer without winter, the year without summer is what I meant to say, where there was snow on the 4th of July in Boston. We talked about the French Revolution, that there are major episodes in Earth's history where there are multi-year cooling events in response to volcanic eruptions that put SO2 into the stratosphere. So taking a step back from that a moment, how does this magma that forms these volcanoes form? Remember, there's three main mechanisms. There's decompression melting. Decompression melting is when you remove the overburdened pressure. So imagine you're in the middle of the Atlantic Ocean. You have this crustal plate on top of the crustal and oceanic plate on top of the Earth's mantle. When that plate gets pulled apart in the divergent plate boundary, the pressure is locally reduced, and that causes the pressure on the underlying rocks to be reduced, which actually allows decompression melting. That's the most voluminous amount of volcanism occurs by decompression melting at every divergent plate boundary around the world all the time. Okay, so the vast majority of volcanism is performed by this mechanism where plates are pulled apart by subduction on the other end of the plates. That reduces the pressure locally and allows magma to expand, leads to melting and the generation of more magma and then volcanism in those areas. The other two ways, the second one being the most important, being the second most important by far, is that the addition of volatiles to the mantle can actually suppress the melting temperature and allow melts to be generated at lower temperatures. So it's the same concept as the sort of a similar concept, I should say, of ice, where you put salt in there. It actually changes the boiling point suppression, melting point increases. It's the same concept here when you add volatiles such as carbon dioxide and water, in particular, to the mantle. It can cause the melting temperatures to decrease. So that's the sort of boiling point suppression, if you will, and it helps magma be generated. The most common areas you see this is where you have subduction bringing down marine sediments, things that have calcium carbonates and water in the pore spaces, and the devolatilization of those subduction slabs lead to volcanism. Perfect examples of this are the volcanoes formed in Cascadia along the composite volcanoes formed in Cascadia along the Oregon and Washington. And then finally, the third place you see magma formed is hotspots. These are the plumes. Good examples of this are Hawaii, where you have again disturbance at the core mantle boundary that leads to a temperature anomaly, and allows the material to be transmitted from the core mantle boundary all the way up to the surface. Importantly, the hot spots are the only one that do not form, at or very near plate boundaries. They can be, indiscriminately hit a plate boundary or hit in between manifest between in the center of a plate, in a continental plate, or in the middle of the ocean, like they do in Hawaii or Yellowstone, or in Iceland. They happen to be near the plate boundary. Some terminology. The hazards from the various types of volcanic hazards I talk about here. One of them is actually from lava flows, and the two types of lava flow. There's two end members. Really slow moving, blocky lava tends to be very silica rich. It's called aa. It's actually a 2-syllable aa, or aa, against Hawaiian word. And then fast moving lava is called pohoihoi. So obviously the lava flow hazards, fast moving lavas tend to be more destructive because people can actually be surprised by them or be consumed by both. Can cause danger, obviously, but typically human life can be spared by moving out of the way of slow moving volcanism. So I not much vocabulary I'll test you on in this course, but those are so intrinsically tied to volcanism, I've included them. So the volcanic hazards have a broad range, include poisonous gases. We talked about in Cameroon and in the Congo, CO2, carbon monoxide, and SO2, but and H2S. So there's sort of 4 major classes, and actually even acidic gases, but CO2 being the most important, that can displace oxygen, cause asphyxiation. Can be something from magmatic degassing, which leads to severe hazards. This is has killed dozens of people and a lot of livestock over the years. Lava flows, skipping ahead here, lava flows themselves obviously present a hazard. Debris flows, so it can be the explosion of the volcano. From Mount St. Helens, you had a massive amount of ash and debris that was sort of flowing down the side of the volcano. That can obviously do a lot of damage, particularly nearby. Ash falls can, as we saw in the Mount St. Helens example, can extend all the way to central and eastern United States. So Ohio had a coating of dust, Pennsylvania a coating of dust that had to sort of be swept off the sidewalks and the cars after Mount St. Helens. And those ash falls, in some ways can be beneficial in that they bring nutrients in some locations, but in many ways they're often really easily respired materials. They cause a lot of lung damage and cardiovascular and respiratory distress from these things, as well as delivering naturally occurring radioactive material and heavy metals to the areas. So these can cause major issues, particularly closer to the volcano. And then pyroclastic activity is another aspect. These are the sort of the molten rock that is blown out, and probably the best example of this is something like Pompeii, where you see major pyroclastic activity, covering up an area. So I sort of covered this already in terms of decompression, melting, addition of volatiles and hotspots. But the volcanism, again, decompression, melting occurs in the convergent plate boundaries, so that's where the volcanism occurs. Convergent plate boundaries is usually addition of volatiles, and mantle plumes, of course, are tied to those hotspots and that we talked about earlier. And I think I actually already covered this one. One other aspect of volcanism, I might have this down the oceanic process, I can't remember where I put this, is remember that the climate forcing implications of volcanic eruptions can also be related to iron, leading to rapid increases in photosynthesis by fertilizing the open ocean, which can lead to global cooling. So in general, by and large, volcanoes tend to, they have complex relationship with climate because they increase CO2 as they degas as well, which can warm the climate, but often by fertilizing the ocean and introducing SO2 and ash dust into the stratosphere can lead to cooling. So many of the key examples of where volcanic emissions dramatically changed the climate, or the climate for a short period of time, have been tied to major cooling events that led to crop failures and things like that. So before I go on, any questions about volcanoes? Well, I appreciate the thumbs up. Unless I see a question, I'll keep going. Um, so I guess the next topic we discussed was oceanic and coastal processes. Um, some of the basics I want to make sure you remember here: the wind energy is ultimately what drives ocean waves. Um, Tides are driven by the moon. They're kind of constant on 6 hour and 13-minute cycles of high and low tides. But really, the tides, they can be major changes in tides, but they don't really do a lot of damage. All the ecosystems are well developed to handle that kind of constant cycle. But waves actually are where most of the damage that are related to many of the hazards related to ocean processes are tied to waves. Waves are driven by wind energy, so that's certainly true and something you want to remember. And waves are formed by the wind energy blowing across the surface of water and basically transmitting that energy to the body of water. Waves can be really important for natural hazards tied to coastal processes because they can erode beaches, they can erode coastlands, and as we talked about, you know, trying to push together the rivers and the oceans in the last two discussions, in areas where sediment starving has occurred, where river channels have been augmented to prevent um, flooding and control the release of sediments, reductions in the amount of sediment getting to deltas and getting to near coastal barrier islands, barrier channels have actually allowed beach erosion to sort of perpetuate quite a bit. And as a result, you've seen major hazards tied to beach erosion and erosion of coastal lands. Um, Back to the waves themselves, the size of the waves, and as a result, the proportional to the risk associated with the waves hitting an area, are tied to the velocity or the speed of the wind. Obviously, I think most of you would recognize the faster the wind blows, the more energy that can be transferred, and as a result, the greater influence the waves have on the wave size. The duration of the winds, a puff of wind versus a sustained winds. You often hear that sustained winds above certain threshold for tropical storms and cyclones. So the duration of the wind, if it blows longer, can cause, obviously, to transmit more energy. And then the fetch, or the distance the wind blows. Something, a wind blowing a longer periods, longer distances, also increase the amount of wave activity. So longer fetches are typically tied to bigger distributions in high and low pressure systems over greater areas. That sort of typically implies a massive storm event. So as a result, obviously, there's a direct tie between major storm events like tropical storms and cyclones and the amount of wave damage that occurs from those activities. So waves are a major issue with cyclones and hurricanes, obviously. One of the things we highlighted a bit, talking specifically about New Orleans and Houston in regard to Katrina and hurricanes Katrina and Harvey, are that the effects of cyclones and hurricanes today are still a fairly controversial issue in the climate change debate, which at this point, I think most of the science has borne itself out. A lot of people point to the fact that the number and frequency, and the intensity of hurricanes hasn't changed, statistically significantly, and point to that issue as being something that implies climate change isn't real, or that the risks haven't really changed. But a few of the things I wanted to highlight here are that the impact, the effects of those cyclones, hurricanes, typhoons, depending where you're located, have actually changed quite dramatically. And this is sort of, independent of the climate change discussion. The reason that these effects have changed is because basically tied to population growth. One, as we talked about earlier in the semester, population growth has increased dramatically, but secondarily, the majority of the world's people live, close to the coastlines, and that the actual percentage of people living in coastal areas has increased. It's not directly tied to population growth, but just in terms of, land use decisions. There's unprecedented increases in the number of folks living near coastlines in the United States, compared to how it was before. The other aspects is that as more people move towards those coastlines, the way we utilize land there has changed. So, putting up buildings, putting up roads, parking lots, all that sort of impervious surfaces tied to infrastructure and population and population growth lead to the expansion of impervious surfaces. And as we talked about a bit, the capacity of groundwater take on some of the water from major rain events, mitigates a lot of the hazards and gets a lot of the water, about a third of the water typically in an average setting, away from its potential, removes its potential to damage infrastructure or harm humans. But the alternative is that when you expand impervious surfaces, that water has to overland flow and actually cause it to accumulate more in certain areas, in addition to not being able to get into the ground. And that's been a major change in the damage from major rain events or precipitation events like tied to cyclones. The third component, particularly relevant in tied to land use change in Hurricane Harvey, but it's true across all parts of the world, is that we've seen a loss of erosional vegetation. There's been major efforts to keep transportation corridors open and free of entanglements. There's been major land use changes on beaches to put in more housing and things like that. And each of them have removed. We talked about switchgrass, which is that really long, deep rooted grass that actually is well adapted to live in sort of saltwater brackish environments, but also has a major potential to reduce erosion because of how deeply rooted its roots are. So all these factors have been particularly relevant in Katrina and Harvey. One factor I would put here is that, again, in Katrina is the loss of barrier islands, the loss of the starvation of the sediments from the delta have contributed to greater issues in Katrina as well. But all those are major reasons why the hurricanes are having greater impact in modern times. So I've already alluded to this, but coastal erosion is a major issue for infrastructure along the coastline. This is pipelines, roads, houses, all these things. Every time we're starving sediments from reaching the deltas and seeing the deltas prograde into the ocean, which create barriers for waves and wind and storms. That enhances the likelihood of infrastructure damages or loss of human life. And most importantly, or not most importantly, but most consistently, it leads to direct coastal erosion, which pushes that barrier back towards population centers each day. So we talked about that in terms of New Orleans, that the coastline is marching towards the city because we've changed the corridors and the river channels along the Mississippi River that have allowed have prevented sediments from getting out and allowed more erosion to occur. So particularly a problem in New Orleans, but not uncommon in many parts of the world. Staying on the topic of the oceans, nutrient delivery to the oceans are most abundantly in a mass balance driven by upwelling. Again, that's where wind drives surface waters away from an area. Offshore winds drive it away from in certain areas, drive it away into the open ocean. That causes the water to mound up in other areas. As a result, there's a mass balance where the water will sort of come up from greater depths. That brings cooler, often more nutrient-rich waters to the surface, and is really important for catalyzing photosynthetic activity. The other major areas where nutrients make their way to the global ocean and allow phytoplankton to grow are in deltas. Rivers carry a lot of nutrients, both natural and anthropogenic, to the oceans. Aeolian or windblown dust. We talked about the Gobi Desert and Sahara Desert have major areas of enriched primary productivity into the oceans because of dust that gets out there. Groundwater, and then of course anthropogenic pollution, typically through rivers and also through groundwater, deliver nutrients and stimulate primary productivity. I think I've already alluded to this, but again, coastal erosion is enhanced by lack of sediments reaching deltaic environments. And I guess we've already kind of alluded to this, but nutrient-rich waters are the key thing for stimulating growth of phytoplankton. The reality is phytoplankton have plenty of sun in almost all the global ocean. There's not shade there. The photic zone gets sun down most of the world. There's clouds, of course, but almost all the areas get enough sun for phytoplankton growth. There's typically, we talked about the Redfield ratios of carbon, nitrogen, phosphorus, and iron. The reality is that carbon is never limited. There's always enough carbon, particularly inorganic carbon and CO2 or bicarbonate or small amounts of formic acid and other organic carbons in the ocean. The limiting factors are, in some cases, nitrogen, but in reality, in the global ocean, nitrogen is typically abundant enough. Most of the phytoplankton growth depends upon either phosphate or more likely um, iron levels in the ocean. So there's great concerns about the role of iron getting from continents to oceans in terms of driving phytoplankton growth, and even a discussion about the fact that the delivery of iron of labile iron to the global ocean might be an important factor for stimulating phytoplankton growth and drawing down CO2 and sort of acting as a solution to climate change. So the goal here is that addition of iron can enhance primary productivity, and clearly that's eliminating nutrients. So the addition of iron having a potential to enhance primary productivity is definitely true. I've already covered that most Americans live in coastal areas, but other hazards besides waves, of course, are tied to rip currents, coastal erosion, tsunamis, and cyclones. I think at this point all those are sort of been covered. So any questions on coastal oceanic and coastal processes before I move on? I'll assume everybody's still sleeping or has it down. So I'll move on to rivers and flooding. So rivers and flooding. This is only really the material covered till Monday, and I promise you what's going to be on the quiz and rivers and flooding will be directly tied to the lectures from Monday and the materials here. Even though I tell you the worksheets are designed to be very much aligned with the quizzes. I kept the exam questions from rivers and flooding to be very closely tied to Monday's lecture and to particularly the review questions. So two major type of rivers are bedrock rivers and alluvial rivers. If you want to know which type it is, you really need to just go to the river and look at the river channel. Again, the river channel is the area we'll talk about in a second where the main pathway of fluid flow, often with a river water flow, often with banks. And if you look at the banks or the bedding of that river, if you see rocks and you see solid rock formations, that's a bedrock river. If you see loosely sorted sediments that aren't lithified, that's an alluvial river. Okay. In general, bedrock rivers tend to have topography, enough energy to keep rocks moving along. They don't happen to be nearly that steep. You can see plenty of bedrock rivers in areas like the southeastern Ohio or near the Appalachians. Alluvial rivers, when we're talking about the Appalachians, are down on the fall line or near the coastal areas where it's flat, meandering, sediment-filled rivers. But being able to differentiate those two are probably going to show up on the quiz or on the exam rather. And the three terms I introduced: river channels are the areas of fluid flow. The floodplain is the area that gets delivery of flood sediments deposited by floods. Overbanked flow deposits that bring water and sediments lead to poorly sorted alluvium around the rivers. That's the floodplain, and those actual sediments are called floodplain deposits. So the channels, fairly obvious, what we think of as the river or the creek or the stream. The floodplain is the area around that. It usually looks pretty flat lying, has low-lying vegetation often, and it's often covered by loosely defined sediments, and those sediments are actually called floodplain deposits. So in terms of, we've alluded to the fact that deltas can be sediment starved, and that the sediment load is really important to basically keeping progression of deltas and preventing beach erosion. But we sort of introduced here in terms of the rivers discussion what that sediment load consists of, and really there's four terms, but there's really three components. So the term that's all encompassing is the total load, and that total load is just the total quantity of sediment carried in a river, and it includes the next three components I'll introduce: the bed load, the suspended load, and dissolved load. And it's the summation of all the material other than water brought to the delta. It can be a lake or more commonly an ocean, or into another river. The total load is basically all those components that are transported by water itself. Now that's not, you notice here, it's only dealing with sediment load. It's not dealing with water. We're going to talk about water and the flux of water in the next lecture or later today if we end up having time. But let's get into those three components. So the bed load is the material that actually is moving along the bottom of the bed. Typically, the bed load is higher in bedrock rivers, but there is a bed load in both bedrock and alluvial rivers. And most of the bed load is material that moves by sort of bouncing and rolling of particles at the bottom of the channel. In alluvial rivers, that can be really fine-grained silt or clay or sand. More commonly in bedrock rivers, it's actually can be things that range from boulders down to gravel, down to gravel or even sand itself. But it's a material that's sort of carried along. It's usually typically too heavy to be not settle out of the water. It always settles out of the water and sort of moves along the bottom. But we tend to think of the bed load being a higher percentage in the bedrock rivers. By and large, it's usually a pretty small component, very small in alluvial, less than 10% of the load in bed loads, and again, mostly composed of sand and gravels. Most times, the silt is such a small component because it stays suspended in the water unless the water is moving really slowly. So the suspended load is actually typically tied to the small grain, is always tied to the small grain fractions. It's mainly silt and clay, some fine grained sand. And basically, these are the particles that are small enough that their density doesn't allow them to sink through the water column faster than water is actually flowing and carrying them along. And the suspended load typically accounts for 90% of the total load or more. And if you've ever been to the southern Mississippi River, looking near New Orleans, something like that, you can see that you often see these muddy rivers, very brown or red rivers. In that area, it's typically brown, and the muddy river appearance often comes from that suspended load, and it can be a pretty high percentage of the total turbidity and total dissolved solids can be just suspended, in the water based upon the density and the relative velocity of the water that keeps it moving along. So most of the significant portion of the nutrients and sediments that are going to lead to progradation of deltas or the balance that can lead to starvation of deltas are really driven by the suspended load, which makes up most of the components. The last component of the sediment load is called the dissolved load, and this is basically things that actually will dissolve into the water itself. So if you imagine sediments getting eroded down from an outcrop of rock or from a farm field, there are things like sodium and chloride, nitrates and sulfates that can dissolve very readily into the water and stay dissolved in the water. And that's the chemical solution. On a mass balance, it makes up an incredibly small, less than 1% of the balance of the total load. But obviously, dissolved components can be very important for stimulating chemistry, and as a result, these components are really important for stimulating, phytoplankton growth, for nutrient delivery, and can be really important for like ecosystems and biological life along rivers. But yet they make up a relatively small component of the total amount of sediments that actually reach, areas from the river load. So, any questions on rivers before I move on to some example questions and open it up for just general questions? All right. So the few example questions I have here, I think the answers are self-explanatory in the fact that I highlighted them in green, but a few examples. Which type of volcano typically contains the lowest silica content? Shield volcanoes, they flow. Think about it flowing out, if it flows out easily, that's a low silica, low viscosity, and that's a shield volcano. Again, high silica content, you pour it out, it's like peanut butter, doesn't go anywhere. That tends to be a composite volcano. So the low silica content and largest, most massive, flat sloping are shield volcanoes. Land use change can lead to changes in river profile and affect the frequency of floods. Land use change is a major aspect of the hazards tied to rivers and ocean processes such as cyclones. So this is true, and I did talk about this at the beginning of the rivers. I'll talk about this just a moment here, just to highlight things I think are important. But the key thing here is that the hydrologic cycle is driven by solar radiation. Remember that the hydrologic cycle, as we talked about in Monday's lecture, is all driven by the sun's radiation. That leads to evaporation. Most of that occurs in the global ocean, mainly because it's, massive amount of the Earth's surfaces. Also because salt water evaporates a bit faster. But as a result, most of the evaporation and most of the hydrologic cycle is catalyzed by solar radiation evaporating ocean waters. Of course, that's the same is true for lakes or water in sediments. So evaporation brings water vapor up to the atmosphere. That water vapor basically will condense on cloud condensation nuclei. It won't promise I won't test you on that, but that's how it works. And then the low pressure systems occur that are driven by the addition of water vapor, which lowers the total mass of or the mass of a volume of water or volume of air, lowers the pressure, causes pressure variations, cause wind to transport water-rich parcels of air into different areas. Much of that precipitation, much of that air as it moves away can cool or it can oversaturate with water vapor. That leads to precipitation. Much of that precipitation will occur over the ocean, and of course, a lot of it occurs over land when you see the body of a parcel of air, sort of at saturation, moving on the land. And when it gets over land, it gets dry enough, or it experiences changes in elevation. So as a result, either it can become oversaturated with respect to the increased temperatures over the land and cause precipitation events, or we mentioned the idea of adiabatic lapse rate, where mountains and topography changes can cause the air mass to move up. That air mass moving up can cause cooling, and that cooling will eventually cause precipitation events. That precipitation, once it falls, whether it's rain, snow, sleet, or hail, falls on land surfaces, and then from there, three options are either it percolates or infiltrates into the ground, it flows overland by runoff or surface runoff into lakes, streams, and rivers or the ocean, or it gets evaporated again by either being evaporated from one of those bodies of water, from soil itself, or also by plants basically pulling the water out of the subsurface and respiring it into the air, which we loosely lump all those together, called evapotranspiration. Quantifies the amount of water that goes back into the atmosphere without us really even seeing it reach the subsurface. So the material we talked about, the hydraulic cycle on Monday, is fair game, but knowing solar radiation drives the process, knowing that the fate of precipitation is either infiltration into the ground, runoff, or another form of evaporation is more or less in line with the level of knowledge I expect you to have for this particular midterm. But you'll see a question or two about that. Don't stress about it too much. So those are the example questions. Again, 30 questions, multiple choice, true, false. It's available at 12:01 tonight, or technically Thursday morning till Saturday. No in-person lecture on Friday, or no new in-person lecture on Friday. If anyone has any questions, feel free to email me. I try to be really responsive to emails, and I'll try to get back to you if anyone has any questions. But if you've been doing well in the quizzes, or the worksheets as we call them, I don't think you'll have, and you do well in the first exam, which is true for almost everyone. I don't think you'll have too much trouble. Just to remind you, the midterm 2 is online, and it's accessible through the quiz tab on the Carmen page. So I'll stop talking. Does anyone have any specific questions for me? Well, you're certainly welcome. I'll hang out for a few minutes in case there's any questions, but otherwise, I think everyone will do great.